Okay, so welcome back. Hope everybody enjoyed the long weekend. I did something fun for Labor Day. So we have this class and then we have another, few days until we come back for Monday's class. So the plan for today is to finish up a couple of little details in 2.4, maybe go through a slightly more interesting problem, and then talk about infinite limits really quickly. So again, 2.4 is, kind of on the borderline between the kind of Calc 1 through th 3 sequence and maybe like a theoretical calc course. So we're not going to, follow these ideas in 2.4 through the rest of the course. We saw in section 2.3, we had some limit properties, and then we're going to introduce some more properties or an important property and some consequences in 2.5. So after this kind of little deviation into 2.4, talking about the epsilon delta definition of limit, we're going to kind of go back to regularly scheduled programming, so to speak, and look more at some properties of limits and continue on with this kind of, I guess you could call it like a more algebraic approach than, say, a theoretical approach. And certainly we don't want to lean on that empirical approach that we kind of started off with. So that is the plan for today. We probably won't get through all of continuity today, so I plan to kind of start Monday's lecture with just wrapping up continuity. It is an important topic, so I think it's okay to bridge two lectures, come back Monday, remind ourselves a little bit about it, go through a couple more examples, and then move on. The quote of the day today is, I guess, kind of a comic of the day. It's from XKCD Comics. They have fun, kind of nerdy comics. And this is comic 2899. And the one stick figure is saying, when a metric becomes a target, it ceases to be a good metric. And the other stick figure says, sounds bad. Let's offer a bonus to anyone who identifies a metric that has become a target, thereby, making a target of metrics that have become targets. And um, so where does this come into play? Well, there are a lot of examples. One kind of classic example that I don't know how historically accurate it is. It's in a couple of different phrased in a couple of different ways that I've seen it. But say, for instance, that there are rats in some city, there's an abundance of rats. The folks in the city want to get rid of the rats. So they say, okay, we have too many rats. We want to get rid of the rats. It would be nice if, the people in the city would help cull the rats. Um, so we'll say, okay, we'll give you $1 for every, say, rat tail that you bring in, kind of as evidence that you've killed a rat. Um, and that seems to work well, right? We have too many rats. We'll pay you to, turn in evidence of dead rats. Presumably, the more dead rats evidence that we get, the fewer rats there are out in the population. But people might realize that it's actually more efficient to breed rats, kill them, and then turn in their tails than it is to actually go out and collect, hunt or trap or whatever rats in the wild. So it doesn't actually, um, so the metric, the rat tails turned in, isn't really tied to the target anymore. There's a way to game the system to make the metric look good, and the target, getting rid of the infestation of rats, is unaffected. You see this in in business often. So you might say, okay, I have a company. I want to incentivize my employees to, say, do a certain thing, maybe to provide better customer service. Um, we have a metric that says how good our customer service is at this point, and we survey our customers, say, how satisfied are you? They come back and we say, okay, we got a 3-star average rating out of 5 stars. We're not happy with that. We want to improve customer service. Well, one thing they might do is they might say, okay, if we go from 3 stars to 3.5 stars over the next year, everybody gets a big bonus. Well, you could do that by providing better customer service, but you could also do that by, say, adjusting the survey or changing who gets the survey, or, right? There are a lot of ways to game the system to make the number of stars go up that doesn't actually help the customers or might even hurt the customers. Um, so, on the other side, like, you want success to be measurable so that you know if you're going in the right direction or not. And it becomes very hard to tease apart whether your metric has become a target or not. Um, But certainly if you just say, if you say to your employees, make this number look good and we'll reward you, or even worse, if you say, if this number doesn't look better, we'll fire you, or, some bad thing will happen, people will, burn down the company to make that one number look good. The company could end up being completely gutted, but having this one number look stellar and everything else is falling apart. So that's just a kind of a cautionary tale. It's kind of a behavioral finance idea, which is probably why I think it's an interesting idea. That we have to be really careful when we set up incentive structures to realize what are the targets, what's the actual thing I want to change, and what are the metrics, what are the things that are evidence of change. I want to focus my efforts on the target and then hopefully see that come through to the metrics rather than focusing too much attention on the metrics and just making that number look good. Okay, so continuing with 2.4, we introduced the idea last time of the precise definition of a limit. Just a quick recap. Limit x goes to a if of x equals L, a real number, means the following. We have this little kind of boilerplate here, but the real crux of the definition is this part, that for every epsilon bigger than 0, we typically think of epsilon as a small number. So for any small positive number that's chosen, we can find a delta bigger than 0. Typically, that's going to be a function of epsilon, such that if x is within delta of a, of the limiting value, then f of x is within epsilon of L, the proposed limit. And we went through a couple of examples last time. We're going to look at a more challenging example this time. So we saw that last time kind of the structure of these proofs, and I just realized I'm hitting enter a bunch, and that's probably messing up my little picture that I drew down here. So give myself a little extra space. Yeah, unfortunately, when I draw things in OneNote, it tends to, it doesn't really stick to the text as well. Let me actually try to, let me see if I can do this. Sorry, just give me 1 second here. I forgot that I had this drawn picture until just now, and I don't want it to get too messed up. I'm actually going to screen cap it and paste it. And then erase it. I think that will actually work a lot better. So sorry, I should have done this before class, but it just hit me as I was hitting enter a bunch of times that I had this down here. All right. Now that shouldn't get messed up whenever I give myself extra space as needed. Okay. So we saw that the structure went something like, start off by basically writing this line with the particular a, f of x, and L that I'm interested in, and then kind of go off to the side and scratch work and kind of reverse engineer it. Try to figure out how I can make this bit over here look kind of like that bit over there. Then I can line up what my epsilon and delta, what their relationship has to be. What does delta have to be as a function of epsilon? And then I can basically take that reverse engineered set of lines, reverse them, and then that's my proof. So that was kind of the structure. So if I want to prove that limit x goes to 2 of x squared equals 4, what I want to prove is that given epsilon bigger than 0, or sometimes we say something like let epsilon bigger than 0 be given, something like that. Given epsilon bigger than 0, pick delta equals, and this is what I'm not sure about yet. How should I pick delta? And with that choice of delta, I want it to be true that if 0 less than absolute x minus a, and let me put in, instead of a, I'll put in x minus 2 less than delta, maybe I'll say, then 0 less than x minus 2, absolute x minus 2 less than delta implies absolute f of x is x squared minus L is 4, our claimed value of the limit, less than epsilon. So this is what I want to show. The main implication that I need to show here is this one. I want to go from the absolute x minus 2 less than delta to absolute x squared minus 4 less than epsilon. I start with the right-hand side, reverse engineer it to get myself back to the left-hand side, and then I basically just flip that line of reasoning, and that's my proof. That's the rest of my proof. So let me come over here to some scratch work. I want absolute x squared minus 4 less than epsilon. And what I'm allowed to do is I'm allowed to restrict how big absolute x minus 2 can get. So I need to make this look like absolute x minus 2 less than something, where that something has something to do with epsilon and maybe some other numbers. So my goal is to get absolute x minus 2 less than something. That something is what I'll pick for my delta. Okay, well, one thing that I see that I could do is I could make this absolute x minus 2 times absolute x plus 2. Now, this has gotten me one bit that looks kind of like what I want, but I have another bit that I'm not sure what to do with. I have to do something with this absolute x plus 2. Now, last time, this kind of just turned out to be a number, a constant number. I think like maybe something like 5 or something. We could just divide through by it. But here, this is a variable. I'm going to make use of the properties of my limit here that I'm taking the limit as x goes to 2. In other words, I can restrict consideration of my inputs to those near 2. I can pick delta any way I want, so I can certainly pick delta to, say, be less than 1. So here we'll say assume that x is in the interval 1 to 3. Or in other words, assume delta is less than 1. Now, if we wanted to be super particular, when we get to the bottom, we would say pick my delta to be the minimum of 1 and whatever I come up with. If I wanted to be really nitpicky about it, that's something that we would worry about in maybe a more advanced class. But here we'll just say assume that we're restricting our domain to 1 to 3. So assume that delta is less than 1. Since really we're the kind of difficulty of the limit, so to speak, is in showing this for very small epsilons, we're not super worried that if epsilon is really big and we get a really big delta, that it might be bigger than 1. That's not the kind of case that's the kind of hard case to manage. So there is a little bit of some particulars that we're skipping over here, but I think it's good to skip over those so that we're not too into the weeds. But if x is between 1 and 3, then x plus 2 in absolute value is between 3 and 5. That means that absolute x minus 2 times absolute x plus 2, what I have on the left side up here, that's less than, well, absolute x minus 2 is non-negative, times the biggest that absolute x plus 2 can be when we're under this restriction is 5. And that's what we're going to set less than epsilon. So if we can choose a delta that imposes that absolute x minus 2 times 5 is less than epsilon, then certainly it'll be true that absolute x minus 2 times absolute x plus 2 is less than epsilon. But to force absolute x minus 2 times 5 less than epsilon in a manner that looks like this line down here, that looks like what we can impose using our delta, well, we just divide by 5 now. So how am I going to choose my delta? I'm going to choose my delta to be epsilon over 5. Now, this is what I want to say here, but I haven't actually said it yet. I just kind of sketched this out so I knew where I wanted to go with it. So let me erase this bit. So now I can say that, well, with this choice of delta, epsilon over 5, choosing absolute x minus 2 strictly between 0 and delta implies, well, what does that imply? It implies that this is my next line up. Well, oops, this one. This is my next line up. It implies that absolute x minus 2 less than epsilon over 5, which implies that absolute x minus 2 times 5 is less than epsilon. And then we can say if delta less than 1, x is in the interval 1 to 3, then this implies that absolute x minus 2 times absolute x plus 2 is less than absolute x minus 2 times 5, which is less than epsilon. And this implies that absolute x squared minus 4 is less than epsilon. And maybe we can drive it home even a little more clearly, which implies that absolute f of x minus L less than epsilon. And that's exactly what we needed to show. When absolute x minus a is strictly between 0 and delta, then absolute f of x minus L is less than epsilon. So we can see this one was a little more challenging because we were able to get something that looked like absolute x minus 2, but we also had some extra stuff that wasn't so easy to deal with. I can't just divide through by x plus 2. I can't make my delta epsilon over x plus 2 because delta is allowed to depend on epsilon, but not x. Right? Epsilon is what's given. X is varying in this, small interval surrounding 2. So I do have to be careful about that. So again, this was a little more nuanced proof. We had to do this kind of extra little step here. But the reason I think this is a good proof is that even though we're not really going to be doing proofs like this from this point on, we will be making use of the fact that we can say, okay, well, I know that the limit is a local property, local to the point A, where x going to A. So if I have some big complicated function, I can choose to ignore very much of that function and only look at what's going on near A. I can pick a small interval around A, kind of throw everything else out. If I have a piecewise function or something, I can only look at the piece or pieces that that are near A and get rid of all of the rest of it. So we will use this idea quite a bit, even if we're not, using it in the epsilon delta definition as we did here. Okay, we also had previously introduced the idea of an infinite limit. We have, again, some boilerplate here that, we have a suitable function and all of that kind of thing. When we say limit x goes to a f of x equals infinity, what do we mean by that? Well, what we previously said is kind of that, whatever number that you're interested in, no matter how large positive it is, I can find an input that yields an output bigger than that number. And that was like the kind of got at the idea, but there's a little particular detail that we missed there. So we're going to talk about that a little bit now. What this means is that for every m bigger than 0, we think typically of m as a large positive number here. There exists a delta bigger than 0, positive delta, such that absolute x minus a strictly between 0 and delta, so that if x is sufficiently close to a but not equal to a, for that entire interval, absolute x minus a less than delta, except at x equals a potentially, f of x is bigger than m. So it's not just that I achieve getting bigger than m at some point in that interval, but that no matter what m you pick, I can pick a small interval and my outputs stay above m on that entire interval, except possibly at a. If you pick a bigger m, I can shrink the interval and my outputs will stay above your bigger m on that whole interval, except possibly at a. And of course, an analogous definition holds for negative infinity. For every, say, what would we say, like negative m less than 0, I guess, or something like that. We would say like f of x less than negative m. So let's go through an example where we prove that limit x goes to 0 of 1 over x squared equals infinity. Why should this be true? Well, let's draw a picture. So no matter what potential m we pick, we can restrict ourselves to an interval surrounding 0 that yields outputs that are only bigger than m on that interval. Again, except possibly at 0. If we pick a larger value for m, we just have to pick a smaller interval, and that restriction will yield outputs that are larger than the larger m on that whole interval, except possibly at 0. So what do I want to say here? I want to say something similar to before. I want to say something like let m bigger than 0 be given. Then I can say that I want to choose delta. Some way I have to figure this. Oops, it's not delta of epsilon anymore. This is delta of m now. I want to choose delta in some way, probably dependent on m, so that this implication holds. 0 less than absolute, well, x minus a is 0 here, so absolute x less than delta implies this is what I want to be true. So I'm going to kind of like write it here, but when I come back and actually write out my proof, I'll erase this and I'll show the steps to show that this is true. Implies that f of x bigger than m. Note that f is not inside an absolute value here, because if f was like, say, large negative, I wouldn't want to say that its limit is positive infinity. So we had the absolute value up here because this is representing the distance that the output is from the limit L. But we don't have that here. We want to look at the actual output. And so I want f of x bigger than m, or that means that I want 1 over x squared bigger than m. So this is where I want to end up. And I do the same kind of thing. I reverse engineer it over off to the side. I want to start with 1 over x squared bigger than m, and I want to end up with absolute x less than something. And this isn't too bad. I multiply by x squared, I divide through by m. So I get well, let me just say it this way. You get x squared less than 1 over m. Everything is positive here. I can square root both sides. I started by picking m to be positive. If I square root both sides, I get absolute x less than 1 over root m. And now I see what my delta should probably be. If I choose delta to be 1 over root m, then again, this is what I want to show. Oops, erased a little bit of my delta there. So 0 less than absolute x less than delta, but delta is 1 over root m. This says that absolute x less than 1 over root m, which implies that x squared is less than 1 over m. I can multiply through by m, divide through by x squared. This tells me that 1 over x squared is bigger than m, or in other words, this tells me that f of x is bigger than m, which is exactly what we wanted. So if you pick m to be a million, I need to pick delta to be 1 over 1,000. We can go from minus 1 over 1,000 to plus 1 over 1,000 on the input side, and for that entire interval except 0, we get outputs that are at least, what I say, a million high. And importantly, we stay above that over that entire interval. That's something that we didn't really address before. So for example, if we forget about this piece, forget about the sine piece for now, limit x goes to 0, 1 over x squared, that's infinity. That's what we just saw. Now, what if I had limit x goes to 0, 1 over x squared times sine of 1 over x squared? And if I tried to do some kind of like squeeze theorem-esque thing and say that, well, the sine function just goes between -1 and 1. So really this is going to look like something like this. It's going to oscillate faster and faster as I get to 0, but it's also going to be heading, in a sense, to infinity, right? Something like this. No matter how high of an m you pick, I can always find outputs. If I pick a small enough interval around 0, I can always find outputs that are above that m. But those outputs don't stay above that m on that whole interval. So this limit is not infinity. This limit does not exist. Because if I pick some small interval, and if you pick some m, I pick some small interval, I can pick an interval small enough that I'll occasionally get outputs that are above the m that you picked, but I'll also occasionally always have outputs resulting from inputs in that interval that are below the m you picked. So we don't stay above m on that whole interval. So it's not just the fact that we can achieve an output above m, but it's that we have to be able to pick a small enough interval that our outputs stay above m on that whole interval, again, as always, except possibly at the limiting point. Are there any questions on any of this so far? Okay, so that wraps up our discussion of the epsilon delta definition. Again, these two were maybe, slightly more challenging versions of the problems we did last time. But I hope that we've, one, gained an appreciation for the epsilon delta definition, the kind of under the hood, how everything works. And two, I hope that we have picked up some practical skills as well, particularly, from today's work, the idea that we can restrict the domain to a small interval around the limiting point, and sometimes that's quite helpful. So things like limits are local properties, and things like the derivative is also a local property. So sometimes if we're talking about derivatives, it's helpful to restrict our point of view, our domain, to something near where we want to take the derivative. Teasing some of the material that we'll see at the end of chapter 2, beginning of chapter 3. Okay, we're going to move into section 2.5 now, continuity. So we're kind of shifting gears back to something that's going to feel a little more like the 2.3 material, where we're looking at some properties and how to apply those properties algebraically. So we have a definition. We say that f is continuous at a if limit s goes to a f of x equals f of a. If you think back to your kind of basic algebra definition of a continuous function, what you probably were told was something along the lines of, like, if you can draw it without picking up your pen, then it's a continuous function. That's actually a pretty good characterization of a continuous function. But that's a very kind of geometric feeling statement. Here we have a statement that we can use algebraically. We say f is continuous at a point if limit x goes to f of x equals f of a. In other words, if that plug-in thing that we really are tempted to do, if that actually works, those are the functions that we call continuous functions, or at least continuous at that point. So we can do the plug-in thing if and only if our function is continuous at the point that we want to plug in. Not all functions are continuous, so again, we have to be very careful when we apply this kind of plug-in strategy. We don't want to just apply it, all over the place. We've seen before that polynomials and rational expressions kind of got the thumbs up on their domains, on the rational expressions domains. But we now have a broader class of functions that we can use this plug-in property for. It's important to note, I think, that really this one statement, limit x goes to f of x equals f of a, it really consists of kind of three statements. There's kind of three things we need to check to see if this is true. Well, the first thing is, does f of a even exist? Right? If we're trying to do the square root of -1, that's probably not going to go so well. If we're trying to do 3 divided by 0, that's probably not too good. Does f of a even exist? The other question is, well, does the limit even exist? Limit x goes to a, the limit might not exist. We've seen examples before where we have a seemingly reasonable function, a seemingly reasonable point we're going to, but the limit doesn't exist. There's maybe disagreement between the left and right hand limits, something like that. And then the third thing is, okay, if they both exist, then are the two values equal? So we really are saying three things here. We're saying f of a exists, the limit exists as x goes to a, and that those two values are the same. We want to be careful with that. We really got to check all three of those. We say that f is continuous from the left, or just left continuous, if the left-hand limit equals f of a. And an analogous definition applies to right continuity or continuous from the right if the right-hand limit of f of x equals f of a. And we say that f is continuous on an interval I, or if we just generally say f is a continuous function, what we mean by that is on its natural domain. So like square root on closed 0 to infinity, or, polynomials on the whole real line, things like that. So f is continuous on an interval if it's continuous at each point in that interval. Okay, so let's look at the newly fixed version of the graph that I had drawn here earlier. And again, this is kind of a hand-drawn graph, all of the interesting stuff we'll just assume occurs at integer points, integer inputs and integer outputs. And we want to evaluate each point 0 through 6 for continuity. Is it continuous? Note that continuity overall implies left continuity and right continuity. So if a function is continuous at a point, then it's left continuous at that point, and it's also right continuous at that point. And if a function is both left and right continuous at that point, then it's overall continuous at that point. So we'll look at each of these. We'll say, is it overall continuous at the point? If yes, good, we're happy with that. If not, then is it left or right continuous at that point? It might not be left, right, or overall continuous. It might just be left continuous and not right continuous, or it might be overall continuous, or it might be right and not left. So we kind of have 4 different possibilities for each point. So let's start at x equals 0. Well, pretty clearly we're not overall continuous here, but we might be right continuous here. So let's check. Does f of 0 exist? Well, yeah, f of 0 is 2. So that's one component of right continuity that is checked off. I know that the overall limit at 0 doesn't exist because I can't approach from the left. But is the right-hand limit of f, does that limit exist? Yeah, it seems like it should exist. And it seems like it should also be 2. So the right-hand limit exists and is 2. And are these equal? Yes, they are. 2 equals 2. So we are right continuous at 0. Now, what about at 1? Does f of 1 exist? Yeah, f of 1 equals 1. Does the limit x goes to 1, f of x, exist? Yeah, it actually does. So this exists, this exists. It looks like that would be equal to 3, though. As I approach from the left or the right, my outputs are getting closer and closer to 3. Now, if I plug in 1, I get an output of 1, but remember the limit says you can't plug in the value that you're limiting to. That's like in the definition of the limit. And then is 1 equal to 3? Well, no. So 1 is not continuous at 3. Or I said that completely wrong. F is not continuous at 1. I think I was reading 1 when I wanted to say F and ended up saying 1. F is not continuous at 1. What about at 2? Well, f of 2, well, f of 2 doesn't exist. Right away, we're not continuous at 2. I don't have to go any further into limits. I could see that the limit's going to be 2. Limit x goes to 2, f of x is going to be 2. But I don't have to evaluate this any further as far as just continuity is concerned because f of 2 doesn't exist. I have no chance of being continuous here. What about at 3? Well, f of 3 exists. F of 3 equals 1. So that's a good start. Does the limit as x goes to 3 f of x exist? Well, no, the overall limit does not exist. My 2 one-sided limits, though, do seem to exist. My left-hand limit at 3 seems to be 1. My right-hand limit at 3 seems to be 3. So my two one-sided limits exist. They're not equal, so the overall limit doesn't exist. But I do notice that my left-hand limit exists and equals the function output. So this is going to be left continuous. So we're left continuous at 3. We're not right continuous at 3. And therefore, we're not overall continuous at 3. What about at 4? Well, it kind of seems like f of 4 equals 2. So my function exists there. Does limit x goes to 4 f of x exist? As I plug in values closer and closer to 4, do I get outputs that are closer and closer to some limit? Yeah, it seems like it should be 2. So it seems like that limit exists and is 2. And I see that 2 equals 2. So we're overall continuous at 4. What about at 5? We have a corner here. Does that mess anything up? Well, f of 5, if I plug in 5, I get an output of 1. F of 5 is 1. My function exists at 5. That's good. Does the limit exist? We might be tempted, especially if you've had some calc before, to say, oh, I don't think the limit exists here. But remember, if we're looking at like that idea back at like limits of slopes of secant lines, that might be a problem, but just the limit of the function itself is what we're asking about here. Limit x goes to 5 f of x. As I plug in inputs that are closer and closer to 5, I get outputs closer and closer to 1. That limit exists just fine. So thinking ahead, the derivative would not exist here because of that point. Or whenever we were looking at the absolute value with those kind of secant lines, that caused a problem back in the early stages of chapter 2. But that's not what we're asking about here. There's no discussion of secant lines or anything like that going on. We're just asking about the limit of the function. Yeah, exists perfectly well. And 1 equals 1. So yeah, we're actually overall continuous here as well. And this does kind of fit the characterization that I can draw a V, even though it has a point, I can draw it without picking up my pen. So that also has kind of the feel of being continuous. And then I guess I'll come up here for 6. Well, pretty easy one here. F of 6 does not exist. We are not continuous at 6. Any questions on anything?
It looks like there should be an asymptote at 5, but there isn't.
Um, yeah, I'm not, so 5 is meant to look like, oops. 5 is meant to look like kind of an absolute value, like a corner like that.
Okay, it makes sense now.
Yeah. Yeah. So like a vertical asymptote would, I'd probably try to draw it a little clearer. It would look, you know, something along those lines. Yeah. It is worth mentioning that if you draw functions on a calculator, because it has to just choose for each pixel whether to turn it on or off, the calculator might do something like this, depending on what the settings are set to. And it might be hard to tell that apart from something like this, just because, if these are close together, like it doesn't want to fill in this next pixel. So, um, yeah, I mean, certainly when you're just looking at things visually like this, it can be a little hard to pick apart exactly what's going on. And that's one of the reasons we like to lean on the algebraic structure more than the graphical a lot of the times, is that it's less likely to lead us astray. Yeah. Any other questions or thoughts? Okay, so next up we have a couple of theorems. We're actually making really good time through this. I um, didn't think we would get through that epsilon delta stuff quite as quickly as we did. So theorem, the extreme value theorem, this is a theorem that applies to uh, kind of our fairly narrow scope that we're looking at. We're throughout this course in Calc 1 through 3, we restrict ourselves to real functions, not complex functions. So we're not looking at complex numbers. We're not looking at more general types of kind of sets and things like that. But this actually generalizes very well to much broader areas of math. But the extreme value theorem basically says continuous functions on closed and bounded intervals achieve their extrema. And we're gonna pick this apart and see what each of these pieces means. But a couple notes. It's actually quite important that the interval under consideration is both closed and bounded. Closed meaning that we include the endpoints, and bounded meaning that we don't shoot off to infinity in either direction. If we replace the term closed and bounded intervals with the term compact sets, it turns out that in the real line, the compact sets are equivalent to the closed and bounded intervals. But we can generalize this idea to a much broader idea of compact sets. And this allows us to generalize this similar extreme value theorem uh, to quite a broad scope. So this is actually a very broad theorem. We're kind of like, you know, looking at one very specific application of it. But I don't think I would be too far, I don't think I would be speaking hyperbolically if I said that this is one of the most important theorems in math, at least in kind of analysis and kind of math related to things like calculus. Okay, so what do we mean by this? Well, continuous functions, we just discussed the ideas of continuous functions. What do we mean by extrema? Well, an extremum is a maximum or a minimum. And what does it mean for a function to achieve its extremum? It means that if, say, capital M is the maximum of f, then there is, let's say, an input c such that f of c equals m. This is what it means to achieve its maximum. Now, you might say, I mean, if I had an interval that's not closed or not bounded or a function that's not continuous, I mean, at first glance, it kind of seems like this should be true regardless of whether the function is continuous or not, whether or not our interval is closed or bounded. You just take all of the inputs that you're allowed to plug into the function, you plug them all in, and you take the biggest output, call that the maximum, take the lowest output, call that the minimum, and there you go. Now, I suppose if we only had finitely many things we could plug in, that would be fine. But we have these kind of strange cases. What if I took a nice continuous function, like say 1 over x on 1 to infinity? Now, on 1 to infinity, 1 over x is a nice continuous function. It blows up at 0, but we're staying away from 0. Well, the maximum output, we'll call this f, the max of f is 1, right? That's the maximum output. We can't plug in any value into f and get an output bigger than 1. And we note that f of 1 equals 1. It achieves its maximum. What's the minimum of f though? You might say that you think the minimum of f is 1/10, but I could plug in 11 and get an output of 1/11. That's smaller than your claimed minimum. If you said you think the minimum is 1/1,000,000th, I could plug in an input of 1,000,001 and get an output that is still in the interval under consideration and is a smaller output than the one you claimed. So the one, the 1/1,000,000th couldn't be the minimum. In fact, any positive number, 1 over k that you claim to be the minimum, as long as it's bigger than 0, we'll just plug in k plus 1 and you get a number that is below 1 over k. So any strictly positive number cannot be the minimum. So the minimum cannot be strictly greater than 0. We kind of want the minimum to be 0, right? We kind of like gut feeling want to say the minimum 0. So 0 is what we might call like the greatest lower bound. It's a lower bound because there's no input that we can plug in that hits 0 or goes below it. So it is a lower bound, and any greater potential lower bound would have to be a positive number. And we know we can plug in a large enough input to get below any positive number. So this is what we might call something like a greatest lower bound. It's kind of like what we want to be the minimum. But the problem is that f of x equals 0 has no solution. There's no input that can yield an output of 0. In any other lower bound that's positive that you might posit, you might say, okay, I think this is the minimum. I can go a little bit further out to the right and get a smaller output. What's the problem here? The problem here is that we used an unbounded interval. The boundedness of intervals is important here. And this 1 over x example is a counterexample. If we said, I don't think we need to have a bounded interval, we can look at this example and show that with an unbounded interval, we have problems. Now, there might be some, like say sine of x on 1 to infinity. Well, okay, the max is 1, the min is -1. It works for some functions if you don't have a bounded interval, but it doesn't work for them all. So we can't say that it's a theorem then. Okay, so what next? Well, let's next look at closed intervals. What if I were to use an open interval instead of a closed interval? Or even a half open interval? What if I were to look at the interval, say open 0, even to closed 1, and we use the same function, f of x equals 1 over x. 1 over x gets like, I think the most airtime of like almost any mathematical function because it's so useful for so many counterexamples. So what do we have here? We go through 1, 1. And on the interval 0 to 1, I guess it achieves its minimum. Okay, it achieves its minimum, but it actually doesn't even have a maximum, right? If I posit a certain value for a maximum million, I just choose a number closer to 0 than a positive number closer to 0 than 1 over a million, and I get a bigger upper bound, a bigger number than the supposed maximum. So no maximum. Note that it is continuous, importantly, on open 0 to 1. It is continuous at any point that, uh, as you start at 1 on the right and kind of work your way towards 0, but not plugging in 0, it's continuous at every one of those points at a half or a tenth or 1/1 millionth or whatever. It's continuous at each of those points. It's not continuous at 0, but we're not plugging in 0, so we do have a continuous function on a bounded interval, but the interval is not closed. It's a half open interval, half closed interval. It clearly doesn't achieve its maximum because it doesn't even have what we might even as like a gut feeling want to call a maximum. So closedness of the interval is important. And if we look at a discontinuous function over a closed and bounded interval, which function do you think we're going to use here? Well, you probably guessed it, 1 over x on, let's choose -1 to 1 closed. We now have a closed and bounded interval, but at this point we have included 0 in our interval. Our function is not continuous at 0. It's continuous everywhere else in the interval, just not at 0. And clearly, I don't think this requires much argument after the last discussion. We clearly have no, so here's that, but no max or min. We're shooting off to plus infinity on the right and minus infinity on the left. Clearly, there's going to be no maximum or minimum output. I don't think there's really any confusion with that. I think the trickiest part is why can't we have an infinite interval for something like this? And as an aside, there is an easier, I wanted to show this because I think it's an important detail, but there's an easier function that you could use to show just this first part, just something like f of x equals x. If you go from 1 to infinity, it just grows without bound. So, but even for a nicely behaved function like 1 over x, and nicely behaved in the sense it's not shooting off to infinity, we still have this problem. Even when it feels like the minimum should be 0, we can never actually plug in an input that yields an output of 0. And that's a very important part of this theorem, is achieving our extreme, being able to plug in an input that yields the minimum, being able to plug in another input that yields the maximum. Okay, any questions so far? Okay, so we have a theorem. If f and g are continuous at A, then combinations of f and g are continuous at A. Note that combinations is not the same thing as a composition. So combination means add, subtract, multiply, and divide, where g is not equal to 0. So combinations of f and g. If I take two continuous functions and add them together, the resulting function is also continuous. If I take two continuous functions and multiply them, resulting function is continuous. If I take two continuous functions and divide them, so long as I don't introduce a 0 in the denominator, the resulting quotient is continuous. So this means if I know a bunch of kind of mini component functions, like little Lego blocks, if I know that these are continuous and those are continuous, then, when I'm modeling, usually I'm using those little blocks kind of put together in maybe interesting ways. In most ways that I put them together in all of these combinations, add, subtract, multiply, divide, so long as I'm not dividing by 0, the resulting function will be continuous if all of my component functions are continuous. We do have to be extra careful when we talk about compositions of functions, though, and we'll handle that next time. So it would be nice if we know what our Lego blocks are, if we know what our individual little component functions that we use to build bigger functions, if we know whether those are continuous. And it turns out these following classes of functions are continuous on their natural domains. Well, as we expect from that corollary from section 3, polynomials and rational expressions, we were explicitly told we're allowed to use the plug-in property there. And that's essentially what characterizes continuous functions. So we know those are continuous functions on their domains. Radicals, so like square roots, things like that, square root types functions or cube root functions, also continuous on their domains. Just be a little careful with the domain. Things like square root, its domain is closed 0 up to infinity. So at 0, we would think of that as meaning right continuous. But something like cube root, its domain is the whole real line. So make sure you're familiar with what the domains for each of these functions are. Trig functions, again, on the domain, sine and cosine on the whole real line. Something like tangent, we have some vertical asymptotes that we've got to avoid, but otherwise continuous. Inverse trig functions as well, arctan, arccos, and so on. Of course, on their domains. So things like -1 to 1 for arcsine or arccos. Exponential functions, y equals 2 to the x or y equals e to the x, something like that. And logarithmic functions, natural log of x, log base 10 of x, also on their domains. Those are all continuous. So most of the functions that we can think to write down, work pretty nicely most of the time, as long as we're sticking uh, to input points or limiting points that are part of their domains. When we have some kind of edge case or some kind of scenario where we introduce a division by 0, that's when we have to take extra care. So for instance, is tan x continuous of pi over 2? Well, I know that, and if I didn't remember, I know that sine of pi over 2 is 1. Cos of pi over 2 is 0, and tan is sine over cos. Well, sine x is continuous of pi over 2. Cos x is continuous of pi over 2. Tangent of x, though, because we have sine x over cos x, we have to be careful that we do have a combination of two continuous functions, but we've introduced a 0 into the denominator, not continuous. No, because cos of pi over 2 is 0. So just taking a little bit of care, things like when we divide by 0, we have to be careful about that. Let's show that g of t equals t times the Heaviside function h of t is continuous on the whole real line. Recall that h of t, the Heaviside function, is 0 for t less than 0 and 1 for t bigger than or equal to 0. So h looks like this. And then g, which is t times h of t, is going to be, well, t times 0 or also 0 for t less than 0. And then t times 1 or just t for t bigger than or equal to 0. So what does g look like? G's left-hand side looks like this. And we might be a little worried about being continuous at 0. We're supposed to be continuous on the whole real line. But notice that G's right-hand side, when t equals 0, t is bigger than or equal to 0. When it's equal to 0, we plug 0 in for t and we get 0. So we actually fill in this dot and then we take off in this direction. So visually, it looks like it should be continuous. I can draw it like this. Oops. OneNote just tries to be so helpful all the time. And I can draw it like this with, in theory, not picking up my pen, unless OneNote decides to help out. So it kind of feels like it should be continuous. Can we show that a little more carefully? Well, I can do a little trick. I can consider three cases. Case one, t strictly less than zero. Now remember, continuity is a local property. It's a property that applies to each individual point. So if I look at t's that are strictly less than zero, I can restrict myself to an open interval around whatever t concerned with, where that whole open interval is consists of negative numbers. So in this case, I'll assume that I'm restricting my domain to an interval with only negative numbers. So I'll just write it that way. So I don't want to write two lines of math to say I'm only plugging in negative numbers. But in that case, g of t is just the zero function for t's that are for inputs that are close to whatever negative number I pick that I'm interested in. I get exactly zero as the output for all of those. But zero is actually a polynomial. It's a constant. So it's continuous by our theorem above. 0, 3 polynomial. Case two, t is strictly bigger than zero. By a similar argument, I can restrict myself to considering only positive inputs. I can pick a small enough interval around the value under consideration, since it's strictly positive, that interval only has positive numbers. So I'm only plugging in positive numbers. In that case, g of t is t. This is also a polynomial. So g is continuous for all t's strictly bigger than zero. And then case three, well, the only thing we're missing out is t equals zero, and that's the tricky case. Because no matter how small an interval I choose, an open interval I choose around t equals zero, I'm going to get some positive inputs putting me on this side and some negative inputs putting me on this side. So I'm straddling that breakpoint for this piecewise function. I want to show continuity here. I want to show that I'm continuous at zero. Well, if I want to show continuity at a point, I can go back to the definition. Does g of zero exist? Yeah, sure. G of zero, we're on our second part. We plug in t equals zero. We get zero as the output. G of zero is zero. Two, well, the overall limit, that's a little bit complicated. Let me just consider the left-hand limit. Does the left-hand limit of g exist? Yeah, it does. In the left-hand limit, I'm restricting myself to only inputs below zero. And in that case, g is just the constant function zero. So its limit is, of course, zero. What about the right-hand limit? In the right-hand limit, I'm restricting myself to inputs that are only strictly bigger than zero. But that's the regime where g of t is equal to t. Or in other words, this limit is the same as saying the limit t goes to zero from above of t, which of course is zero. That's t is a polynomial. The plug-in property works. I just plug zero in for t and get zero. My left and right-hand limits both exist. They're both equal to zero. My overall limit exists and is equal to 0. So my limit exists, my function exists at that point, and this 0 equals that 0. So yes, I am continuous at 0 as well. So being able to restrict myself to a small open interval surrounding the point of interest is super helpful when I'm dealing with piecewise functions like this. I can ignore all of the other complicated pieces, or, an absolute value as a piecewise function. I can ignore, half of the side of the absolute value, maybe uh, if I'm interested in a point that's not 0, or if I'm interested in a point that is 0, I can maybe look at one-sided limits to allow me to do, or 0 or the breakpoint of the um, piecewise function. I can look at one-sided limits to allow me to restrict myself in that manner. Okay, so let's look at this example. We have h of x. This is a rational expression, x squared minus x minus 2 over x minus 2, when x is not equal to 2. So what we end up with is we end up with something like this. It's something that like really wants to be a straight line, but has a hole in it at x equals 2 because of this restricted value. So if I just looked at f of x equals x squared minus x minus 2 over x minus 2, this is what it would look like. What I would like to do is I would like to construct a function h of x that takes that and basically just fills in the hole. I want to find the value of c to make h of x continuous on R. Well, I know if x not equal to 2, h of x is a rational expression. You can't seem to write an R. If x is not equal to 2, h of x is a rational expression. Its only domain restriction is 2, and we're not plugging in 2. So continuous. We're continuous for all real numbers other than 2, kind of automatically by our theorem up here. So we're only really concerned with what's happening at 2. If we can fix the problem at 2, we'll be continuous on the whole real line. So at x equals 2, what do we have? Well, if I want to be continuous, I need to show those three things. I need to show h of 2. Well, that's c. That's some variable c. That's what I want to find the value of to make h continuous. Does the limit as x goes to 2 h of x exist? I mean, if I had a function like this, well, there's nowhere that I can put a point to kind of fill in the hole, so to speak. It better be true that my overall limit exists there if I want to just kind of plug that hole with a single point. Well, keep in mind that limit x goes to 2 means that x cannot equal 2. So this is just limit x goes to 2 of that rational expression. But I can do some simplification here. This numerator is going to be x minus 2 times what? X plus 1. And I see my x minus 2's go away, and I get x plus 1. And at this point, I'm taking a limit of a polynomial. But again, from my theorem, polynomials are continuous on the whole real line. So the limit, I just do the plug-in property. This is 2 plus 1 or 3. So my limit exists and it's equal to 3. And then third, I ask, is it true that C, the output from number 1, is that equal to 3? If it is, then I'm continuous. Well, I just set C equal to 3, and then that's achieved as well. I'm continuous at 2, as well as everywhere other than 2. And I'm continuous on the whole real line. So we choose to set C equals 3, and that plugs that hole. Any questions on this one? Okay, and then one last continuity problem for today. So here, oops, change its name to F. So here I have an example where I want to find the values of two parameters, A and B, to make f of x continuous in the whole real line. And here f of x is a more complicated piecewise function. So things like this where I want to do some model fitting, they come up in practice. We might, depending on how much time we have around the beginning of chapter 3, we might do a problem related to highway engineering, where we're looking at, say, an incoming road and an outgoing road like this that are straight lines, maybe have different slopes. And then we want to connect the two with a function that, say, matches at the endpoints and maybe also is kind of a nice smooth transition. So this is an example where I have some rational expression. I have a quadratic where I can change a couple of the parameters, and I have a linear where I can change a couple of the parameters. And I want to change those parameters around. I want to set them to be just right so that everything kind of matches up. And I have a nice transition from one to the next. Now, it won't be a smooth transition like this. It might be a choppier transition, not such a nice transition from one to the next. But at this point, we're just trying to make it continuous, not nice and smooth and like you would want to drive over it. So what is my piecewise function? Right, formatting that off here a little bit. My piecewise function is this rational expression x squared minus 4 over x minus 2 for x less than 2. Ax squared plus bx plus 3 for x bigger than or equal to 2 and less than 3. And 2x minus a minus b for x bigger than or equal to 3. So the first thing we realize is for x strictly less than 2, for x strictly between 2 and 3, and for x strictly bigger than 3, we're continuous in all of those intervals. By nature of this being either a rational expression, when x is strictly less than 2, we're not plugging in 2, it's only domain restriction, or the other two being polynomials, which are continuous on the whole real line. So the only potential problem points are at these breakpoints at x equals 2 and at x equals 3. So let's investigate x equals 2 first. Well, first I want to ask, what is f of 2? Does f of 2 even exist? I see that I'm on my middle piece here, the quadratic. If I plug in 2, I get 4a plus 2b plus 3 for f of 2. So this exists. Does the limit exist? Well, again, we're right at the point where we split between two pieces here. So let's break this into two one-sided limits. Let's look at the left-hand limit first. And I know this is, since I'm approaching 2 from below, I'm squarely in the first piece. X squared minus 4 over x minus 2. I'm avoiding plugging in x equals 2, so I can comfortably just divide out the factors of x minus 2. And I'm left with x plus 2. And this gives me 4. That's my left-hand limit. What's my right-hand limit? My right-hand limit is just, well, to the right of 2, I guess I could be on either the second or third piece, but we know that our limit is a local property. We're only concerned with values of x near 2. So we'll suppose that x is also less than 3. We're not going more than 1 unit away from the point of interest, we'll say. Well, then we can clearly say that we are on the quadratic piece. Uh, yeah, ax squared plus bx plus 3. We know we can apply the plug-in property here because we have a theorem above that says that this is a polynomial, it's continuous in the whole real line, so just plug 2 in, 4a plus 2b plus 3. My overall limit exists only if these two are equal to one another. Let's say exists. That implies that 4a plus 2b plus 3 equals 4. So I'm going to choose a and b so that this is true. If I choose a and b so that 4a plus 2b plus 3 equals 4, my limit exists, and it's whatever that common value is. It's 4 and 4a plus 2b plus 3. And then, of course, that equals the output from f of 2, which is just that same left-hand side. So if it's true that we choose a and b so that 4a plus 2b plus 3 equals 4, then our overall limit exists, f of 2 exists, and the two are equal, then f is continuous at 2. So this is one of our two criteria. We have one equation and two unknowns to satisfy continuity at one potential breakpoint. Now we need to investigate what happens at x equals 3. I'll do this part a little bit quicker. Well, f of 3, we see we're on the third piece here. So that's going to be 6 minus a minus b. My limit again, I'm splitting between two pieces here at 3. So I'm going to split this into left-hand limit and right-hand limit. The left-hand limit at 3, we can restrict ourselves to be close to 3, but to the left. And that's our quadratic. Ax squared plus bx plus 3. And we can use the plug-in property on this polynomial. So this is going to give me 9a plus 3b plus 3. And my right-hand limit similarly, my right-hand limit puts me on this third piece, 2x minus a minus b. And again, I have a polynomial plug-in property, 6 minus a minus b. If I also set these two equal to one another, that's my second criterion. Then my overall limit will be equal to both of these, 9a plus 3b plus 3, but also 6 minus a minus b, which is equal to the function output at 3. So I see my two criteria here are this one up here. Switch colors. 4a plus 2b plus 3 equals 4. And this one down here that 9a plus 3b plus 3 equals 6 minus a minus b. And I just have to solve the system of equations. So let's just do that really quickly here. We'll clean things up a little bit. 4a plus 2b equals 1. And 9a plus a is 10a. 3b plus b is plus 4b. And then 6 minus 3 is 3. I suppose I could multiply the first equation by 2, giving me 8a plus 4b equals 2. So 8a plus 4b equals 2. And then subtract them to get what? 2a plus 0b equals 1, or a equals 1/2. And then I can maybe plug back into the first one up here. 4 halves is 2 plus 2b equals 1. 2b is -1 and b equals -1/2. So as long as I didn't make any arithmetic flubs there, that's my solution. So that's what I would choose for a and b to make this a nice continuous function on the whole real line. Now it's probably not going to be a nice smooth function, right? I've taken a function, whatever it looks like, something like that, or my OneNote is starting to go slow. So whenever I undo, I think it hasn't undone, and then it undoes a little too much. So it goes something like this, maybe, and something like that, So it's not a nice smooth transition, but they should meet. It shouldn't be something like this, and then like jump down to there. If I just picked A and B kind of anyway, I might get something like this and like this and like that, where they don't connect. So by imposing continuity, I make them all connect like this. If we want a nice smooth transitions, that has to do with tangent lines and secant lines and so on. That's for either later in chapter 2 or the beginning of chapter 3. Like I said, we might see a problem like that, an example like that, but it kind of depends on time. That example takes a while to do, so I don't always cover it. Are there any questions on anything so far? Okay, so this idea of continuous functions, super important idea. We introduced the idea today. We got really most of the way through the section. We'll finish up the section on Monday and see it a second time. I think that's always valuable. And then continue on with chapter 2, probably looking to move into derivatives, the first kind of really big, you know, uh, stereotypically calculus topic. So that'll be late next week or early the week after. So if you want to read ahead a little bit, see what these ideas are all about, you can read through the end of chapter 2, 2.7, and 2.8, introduce the idea of derivatives, and then 3.1 kind of really hits the ground running with derivatives. So that's what is coming up. Are there any questions before we break? All right, I will stop the recording.